So the complete list of trig identities goes like this. We're going to start with the Pythagorean identities. And in case you hadn't already figured this out, they're called the Pythagorean identities because they come just from performing the Pythagorean theorem on a unit circle that has been identified as a cosine comma sine value. So they're just the Pythagorean theorem. That's all I'm doing. And your basic Pythagorean identity is the sine squared plus cos squared equals 1 identity. When I did it the first time, it showed up as a cos squared plus sine squared, but addition is commutative, and for some reason when you see it on the cheat sheet and in most textbooks, it usually reads sine squared plus cos squared. It doesn't matter to me. The second one came straight from that one. It was when I divided straight through by cosine, and when I divided straight through by cosine, I got tan squared plus 1 equals secant squared theta. And the final one came from the original being divided out by sine, and when I divide out a sine, I get a 1 plus a cotangent squared is equal to a cosecant squared. Now it's worth noting at this point that all 6 trig functions have been accounted for within those 3 Pythagorean identities. So if you need a substitution for a trig function that happens to be squared, this is where you're going to go. It basically gives you a substitution for a squared form of the functions. The next set of identities that we're going to talk about are going to be the reciprocal identities. From here on out, you've already learned these identities. I'm just making a compilation of them so we have them all in the same place, and largely so you know what they are referred to as. So your reciprocal identities, the identities that flip or multiplicative inverses, are the sine is equal to a cosecant under 1, and conversely that a cosecant is equal to a 1 over sine. The second reciprocal identity is that cosine can be written as 1 over secant, or conversely that secant can be written as 1 over cos. Meaning every one of these is a legitimate substitution when you're looking to simplify. And finally, when you're doing your reciprocal identities, all I'm doing here is flipping. So in case you're wondering why I'm not calling this sine over cosine, that's a different named identity, differently named. And cotangent, just the flip, is 1 over tan. Those are your reciprocal identities. The third set of identities that we're going to have in our list, again, you've already seen these, but they've now been named, is called the quotient identities. And they are called the quotient identities because you have 2 trig functions being divided. And that's where your tan and cotan come in. And the quotient identities are that sine is divided by cosine, and the cotangent function shows up as cosine being divided by sine. Does everybody understand the term quotient in that particular place? You got it? The last set of identities that are not commonly used for substitution, but they can be if you need to be, are your co-function identities. The ones you did last block for homework. And I'm only going to write them out one way, but please remember they can be written in the reverse order, which is to say, I could have put the 90 minus theta there, and I could have put theta here. They are interchangeable. I just don't feel like writing it twice. Likewise, secant of theta will be equal to the cosecant of 90 minus theta, or vice versa. And finally, tangent of theta is equal to the cotangent of 90 minus theta. Now, just putting all those formulas on a list and calling them identities might give you a sense of just how much ground we've covered in the last 2 weeks, because I'm kind of hopeful, don't tell me if it's not true, that y'all knew what I was talking about when I did most of those identities. You had a sense of where I got them from, and we've covered a lot of new trig. To use them is going to look like this. So now I'm going to go back a page, and I'm going to try to use them to simplify. That's not where I want to be. I'm going to try to use them to simplify some of the examples on page 28. I'm going to start with 4b, which is right here. And simplify means effectively try and turn this thing into a smaller fraction. So I'm going to try to start this with a two-pronged set of directions. My set of directions is going to start with, if anything in the original question is squared. I'm not doing this one right now, but just for frame of reference, take a peek at this one. There are squared terms going on in this particular question. And when I see squared terms, what I want you to be thinking about is the Pythagorean identities. The Pythagorean identities are there for squared substitutions. But if nothing is squared, your second prong is going to be just change everything to sine and cosine. Every trig function can be written as sine or cosine. Cosecant is 1 over sine. Secant is 1 over cos. I can write tangent as sine over cos. I can write cotangent as cos over sine. If it's already a sine and a cosine, leave it alone. By making 6 functions kind of narrow or pigeonhole down into 2, I can get them to cancel. And that's going to be my goal. So I'm going to take this thing and I'm going to rewrite it as a 1 over sine divided by a 1 over cosine. Does everybody see where I got that from? Now my goal is to try and make this thing less complicated than it was when I started. So it started as a single term. There's no way in heck I want more than one term in my answer. But it started as a fraction. So I'm kind of hoping to be able to make this into a non-fractional expression. Now it appears at first glance like I'm going backwards, but hang on to your shorts here. I could find a common denominator, but instead I'm going to go back to middle school math and I'm going to treat this like a division statement. You don't actually have to write this down unless you need to know what I'm doing. This is actually a numerator being divided by a denominator, which back in middle school you would have learned to solve by keep, change, change. And in this particular case, not using a common denominator was easier. It was easier to just take the bottom and flip it and multiply. I hope you've all heard the flip and multiply process. And now I have a cosine over sine. But what is a cosine over sine? It's a cotangent. So in the process of making that thing uglier for just a split second, I've now made it a single term that is non-fractional, which is simpler. Everybody follow that? That's one of the two things you're going to be doing with these substitutions. The other thing you're going to do with this substitution is something we've already done. So I'm going to show this question to you the way we used to do it, and then I'm going to show it to you the way we're going to do it now. This question at the bottom of page 28 says, if I've got a secant whose value is -5, and it's in quadrant 3, find the tangent. Well, the way I taught you in the past was to say, if it's in quadrant 3, I'm going to draw a bow tie in quadrant 3. If I know the secant, then I also know the cosine. If the secant is -5, then the cosine is -1/5. Is that a fair statement? And the reason I've reciprocated that is because you tend to work better SOHCAHTOA trig with cosine and sine than you do with secant and cosecant. Now I'm going to take that -1/5 and I'm going to label the sides of my triangle. The adjacent will be a 1, the hypotenuse will be a 5, and one of those two values is negative. It's the 1 because it's going left. It's a direction. I'm going to use those two values to find the third side. Remember, this is the hypotenuse, so 1 squared plus something squared is 25. And I end up with a 24 under a radical, which I'm going to call a 2 rad 6. So rad 24 squared is 24, 1 squared is 1, and 24 plus 1 is 25. In your heads, y'all follow the Pythagorean theorem going on there? That 2 rad 6 needs a little addendum. It's negative because it's going down, and the tangent of this thing would become opposite over adjacent or positive 2 rad 6. Now that's just a recap of what we've already done. Look familiar? With the Pythagorean identities, I have a new option. I'm going to use the Pythagorean identity that best matches what I'm looking at. Which Pythagorean identity contains the trig functions secant and tan? Can you all see it's this one? Both of them are in there. Write it down. Now they told you the secant, so put it in. This is no longer going to be a secant that is squared, but rather a -5 that is squared. Now I have 1 plus the tangent squared is equal to 25. What does that make the tangent squared? Subtract 1 from both sides. It's 24. And when I square root both sides, that means the tangent is the positive negative square root of 24. Last but not least, and probably the only sticky point with these Pythagorean identities, is you can't have both answers. Since tangent in quadrant 3 is positive, my bad. Use the positive root. And I get the same answer both ways. Does everybody follow how I did that? Okay. Most of what we're going to be doing today is going to be practicing simplification. So I'm going to do a few more, and then I'm going to put you at the board and just let you struggle, because it's the struggle where you're going to learn something. I'm going to go back and do 4C, and I'm going to do it on a fresh sheet of paper. And I might even do the one on the next page that I circled for you. That is just a 1 plus a secant on the bottom. I don't know why the line went through it. You ready? Here we go. First thing I look for is there anything squared? If anything is squared, I want to go to my Pythagorean identities. There's not. So my second option is going to be just change everything to sine and cosine. This is already a sine, leave it alone. I'm going to change this to sine over cosine. That's my quotient identity for tan. It's a legal substitution. I'm going to leave my 1 a 1, and I'm going to change secant to 1 over cos. Okay, now I've created a slightly uglier term, but it's something I can kind of simplify because I've got fewer variables. When I started, I had sine and tangent and cosine. Now I just have sine and cosine. So I'm simplifying by making fewer variables here. And what I want to do for this is treat it just like a complex fraction like I would have in September. So what would I do in September? Only if it's one fraction